everyone. In this video, we will be talking about finding extrema of functions. So this is going to be in the derivative application section of the class. So you should have already learned limits, derivatives, and are now using derivatives to tell you things about your original function. So there are two different types of extrema, relative and absolute. And you can remember which one is which by using what these words just mean in English. So relative extrema, we're not finding the extrema on the entire function, but just a specific interval. And absolute extrema, look at the entire function and say, okay, where are my highest points and my lowest points? So just remember, anytime you see the word extrema, that means minimums and maximums. The extreme points on the graph, the highest and the lowest. So there are different ways a question may ask you to find extrema. So they may ask you to find relative extrema, and if you're asked to find relative extrema, that will always be on some interval because we're restricting where we look at the graph. Or we may be asked to find absolute extrema, and one way we can do that is using the first derivative test. And another way we can do that is using the second derivative test. So a question may not tell you have to solve to find the absolute extrema in one specific way, but if it does, there are two different ways we can do it. So in this video, we're not going to be going through these algorithms of how to find extrema. We're just going to go straight to the example. And in this video, we'll just do the example on relative extrema. So we're asked to find the relative extrema of this function on this interval. So the directions above that we did not read over have just been copied down here for each example. So to find extrema, our first step is always going to be finding the critical points of the function, which is where the derivative equals 0. So these are going to be the candidates for what could potentially be our extrema. So we take our function and we just take the derivative term by term using the power rule at each step, and then we set that equal to 0. So remember that whenever we're solving when an equation is equal to 0, we often do this by factoring. So the first thing that we're going to do is we are going to factor out this common term of 4x. So that's the first thing that we look for whenever we are factoring polynomials. So next we see that this is 4x times x squared plus 1, and x squared plus 1 is a difference of squares. So it factors as x minus 1 times x plus 1. And now that this is fully factored, we just set each of these terms equal to 0. So this is something you may have heard as applying the zero product property. And all that means is that we set each part equal to 0 whenever we have multiple things multiplied together that equals 0. And then we just solve this for x. So x equals 0, 1, and negative 1. So one thing that I'm going to point out here is that what we do not want to do, and I'm going to write it here in red for us, is that we do not want to do the following. So some people may not have noticed, okay, I can factor out this common factor of 4x. What some people might be inclined to do is to take this expression and add 4x to both sides. And then we see, okay, well now I can divide by 4x on both sides. And I'm just left with x squared equals 1. And taking the square root gives me x equals plus and minus 1. So we don't want to use this approach. And one reason we don't want to use this approach is that it leaves out the critical point of x being equal to 0. So we know that in math, we can't divide by 0. So that means that we never want to divide by an x whenever we're solving an equation, because that may get rid of a solution x equals 0. So just keep that in mind, that we want to factor instead of dividing our like terms. We want to factor that out instead of dividing it. So now that we have found our critical points, we want to see which of the critical points fall within the interval -1, 2. Because remember, when we're finding relative extrema, we're only looking at a specific interval. So if our critical points are candidates for those extrema, we want to make sure they're in the part of the graph that we're looking at. And they all are. So x equals -1 is our leftmost endpoint here. And remember that when we have that square bracket, that means we include -1 and 2. So -1 is included, 0 is included, and 1 is also included. So all of these critical points are candidates for our relative extrema. So now we want to evaluate this function at each critical point. So these are our candidates for our maximums and minimums. So for this method, all we do is say, let's evaluate the function and see which one is actually the biggest and smallest. So we start off by evaluating -1 on the original function. That is one thing I want to point out here, is that whenever we're finding relative extrema, we evaluate the original function on these points. So this is going to be -1 to the 4th minus 2 times -1 squared plus 3, which is 1 minus 2 plus 3. So I want you to pause here for a minute and think, how would I do this without a calculator? So in your calculus class, you may or may not be able to use a calculator, but if you're not, keep in mind that whenever we are simplifying these things, addition and subtraction go left to right, which means that we do 1 minus 2 before we add 3, so this is equal to 2. So where some people may want to add before subtracting because the A comes first in PEMDAS, but keep in mind addition and subtraction go left to right. So if you haven't seen it before, keep in mind that we can think of the order of operations as a pyramid where M and D happen at the same time and also A and S happen at the same time. It's not the case that addition has to happen before subtraction. Okay, so now we're going to evaluate f of 0, which is 0 to the 4th minus 2 times 0 squared plus 3, which is 0 minus 0 plus 3, which is 3. We evaluate f of 1, which is going to be 1 to the 4th minus 2 times 1 squared plus 3, which again is 1 minus 2 plus 3, which is 2. So we've evaluated the function, the original function at each point, each critical point inside our interval, and now we need to check each endpoint. So even though these aren't normally candidates for the extrema of the function, because they may be the highest point where we're looking. So we just need to make sure we check also the endpoints. So we're looking at 2 to the 4th minus 2 times 2 squared plus 3, which is 16 minus 8 plus 3, which is 8 plus 3, which is 11. Okay, so we evaluated the function at each of these points, and our last step is to just figure out which one's the biggest and which one is the smallest. So the smallest value is 2. So that tells us that both -1, 2 and 1, 2 are relative minimums. So even though there's 2 values where this minimum occurs, both of them now are relative minimums. And the largest value is 11. So that means that 211 is a relative maximum. And that's it. So first off, we find our candidates for extrema. We make sure they're in the part of the graph we're looking at. We just evaluate the function on those points to determine which one's biggest and which one's smallest, and then we write our conclusion. So in this video, all we're going to cover is finding relative extrema. So if you go back to where you found this video, you will also be able to find the videos corresponding to finding absolute extrema using the first and second derivative test.